Okay, 9.3. So 9.3 is where we're going to be looking at applications, if I can spell it. So applications of those first order linear differential equations. I'm going to skip over the first example. You can read through it in the book. It is interesting. It is important. Those are going to be motion problems with resistance. So just look through the book and read through it. So this could either be air resistance or friction, any kind of motion where you have a term that's depending on how fast you're going. So like friction, the faster you go, the more the friction slows you down. With air resistance, the same thing. The faster you're going, the more air resistance there is. So look through those examples in the book. What we're going to do is not motion problems. In this video, we're going to do mixture problems. But a little bit more complicated than you're probably used to mixture problems in algebra class. These are the kind of mixture problems that we're going to be doing. Suppose we have some kind of container. Okay. In this container, it holds so much liquid, whatever that liquid may be, whether it's alcohol or we're going to do a problem here with gasoline or anything that holds a substance in the liquid. What we're going to do is we're going to pump in a different mixture into that liquid, and we're also going to pump out the mixture. All the while, we're mixing the solution so it stays consistent. Okay, but this is kind of the general setup for us. So let's kind of get to the math behind the thing. We're going to set y of t be the amount of the substance. Whether that substance, again, is alcohol or sugar or anything that gets mixed into some kind of liquid. Okay, what we want to do is we want to set up a differential equation y prime. So this is the change in the amount of the substance in the solution itself. In words, this is going to be the rate the substance exits minus, that's backwards. The rate the substance enters minus the rate the substance exits. So this is going to be the change in the overall amount of whatever the substance is. Okay, let's take this a little bit further. So the rate at which the substance enters is always going to be fixed because we're always pumping in the same amount. So this rate at which it enters is just going to be the, I don't know exactly what the right way to say this would be. The inflow rate times the inflow percentage, concentration. Okay, so this is going to be the rate at which the substance enters, how fast the solution is coming in times the concentration of that solution. Same thing for the rate at which it exits. So the rate at which it exits, we're going to have to be a little bit more careful about. So it is going to be the outflow rate. That's going to remain a constant because we're pumping out the liquid at the same speed. However, the outflow concentration is going to change because as we pump a different concentration in, it's going to change the concentration in our container. The way that we're going to calculate the concentration in the container is to take the amount of the substance in the container divided by the total volume of the container. So this will give us that proportion or the concentration of the substance at any given time. Okay, so that's going to be kind of our formula. So our formula is going to be the derivative is the inflow rate times the inflow concentration, almost always both constants, minus the outflow rate, usually a constant, times the outflow concentration. That's the concentration of the liquid at any given time. So let's jump into an example. Because these are so long, I went ahead and wrote it up for us. So if you need to, pause the video and get this all written down. Just to read through it, we're looking at an oil refinery. A storage tank contains 2,000 gallons of gasoline that initially 100 pounds of an additive dissolved in it. In preparation for winter, gas containing 2 pounds of additive per gallon is pumped into the tank at a rate of 40 gallons per minute. The well-mixed solution is pumped out at a rate of 45 gallons per minute. How much of the additive is in the tank 20 minutes after the pumping process? I'd recommend drawing a picture for these questions just because they're so complicated. It's nice to visualize what's going on. So we have our container of gasoline. At the moment, so this is at time zero, at time zero there is 2,000 gallons of gasoline, and inside those 200 gallons is 100 pounds of the additive. In other words, at time zero, the amount of the substance that we care about is 100 pounds. So that's going to be our initial conditions. Okay. In preparation for winter, gas containing 2 pounds of additive per gallon is pumped in at a rate of 40 gallons per minute. That means that this pump that we're pumping liquid into our container is coming in with a concentration of 2 pounds per gallon at a inflow rate of 40 gallons per minute. So that is what's going into our solution. Okay, what's coming out of our solution is going to be the outflow rate, which is 45 gallons per minute. But what we don't necessarily know is that we don't know what the concentration is. We know what it is initially, because initially it would just be taking this 100 pounds divided by this 2,000 gallons. But this is going to change as time goes on, so that means that my outflow concentration is going to be whatever the amount of the substance is at time t divided by the volume at time t. What you usually want to do before you get started is go ahead and find the volume as a function of time. That you get by looking at the inflow rate and the outflow rate. Initially, we have 2,000 gallons. However, we have 40 gallons coming in per minute and 45 gallons leaving per minute. Overall, we are losing 5 gallons per minute. So our volume as a function of t, 2,000 minus 5t. Okay, now we can come down and look at our differential equation. So hopefully you wrote down from this other thing here. It's the inflow rate, inflow concentration, minus outflow rate, outflow concentration. So the inflow rate is it's coming in at 40 gallons per minute times the inflow concentration, 2 pounds per gallon. When you multiply these two things together, the gallons cancels out. What you end up getting is 80 pounds per minute of stuff is coming into our solution. But that's going to be minus the outflow rate, which is 45, times the outflow concentration. We do not know how many pounds of additive is in at any given time, so we're just going to leave that as y. We do know what the volume is as a function of time, because we found that up here. That's the 2,000 minus 5t. Great. This is our differential equation. Now we can ignore all this stuff up here and just solve the differential equation. This is the same stuff we were doing in the last section. This is a first order linear differential equation. So first thing we want to do, step one, is we want to write it in standard form. We're going to write it in standard form by moving the y over to the left-hand side. So I'm just going to add it over and kind of rearrange it a little bit. So this is going to be plus 45 over 2,000 minus 5t times y. That's going to be equal to the right-hand side, which is just 80. Okay. All right, now that we have it in standard form, next thing we want to do is we want to find our integrating factor. So our integrating factor, v of t, remember there's the formula for that, e to the integral of p, which is at 45 over 2,000 minus 5t dt. All right, we could pull the 45 out, but before we do that, to actually solve this thing, we're going to have to do a u substitution. So we'll let u be that 2,000 minus 5t, and then du would be negative 5 dt. So I would divide that negative 5 over, and then that negative 5 would be dividing into the 45. So I end up with e to the integral of -9 over u du. Okay, so this has antiderivative of e to the -9 natural log u. Remember that we would bring that 9, -9 in as the exponent, and then the e and the natural log cancel to be u to the -9. But remember that substituting back in the u is 2000 minus 5t to the -9. Okay, great. All right, next step. Now that we have our integrating factor, we're going to multiply the integrating factor on both sides of my differential equation, and then the left-hand side always cancels out to be the integrating factor times y. The right-hand side is going to be that 80 that was already there times the integrating factor. Okay, now we integrate both sides. When you integrate the left-hand side, it just cancels. Cancels out the derivative. Integrating the right-hand side, we're going to have to do another u substitution. So let's at least write it out. The 80, 2000 minus 5t to the -9 dt. U will let be the 2000 minus 5t again. Du is going to be another -5 dt, which means that my integral, so this -5 again is going to be divided here. So 80 divided by -5 is a number. What is that number? 15? Sure. And it would be negative. So -15. And then this is going to be u to the -9 du. Be careful with the antiderivative here. All right, so that -9 is going to go up to -8, and we're going to divide by that -8. So we get 15/8 u to the -8. Don't forget the plus c. And then you want to plug back in the u. Okay, hold on. All right, I made a little mistake here, and I found my little mistake. 80 divided by 5 is not 15, it's 16. That looks a little bit better. So now we have 16 divided by 8, which is just 2. And then u to the -8 is that, substituting back in the u, 2000 minus 5t. This is to the -8 now, plus c. Okay, yep, so sorry about that. I can't divide in my head. I should have done it in the calculator. So that 80 divided by the -5 from the -5 dt becomes -16. So -16 divided by 8. And then when you divide in that -8, the two negatives cancel out to be a +2 u to the -8, where u is the 2000 minus 5t. Okay, great. So just to kind of recopy down what we have the left-hand side, 2000 minus 5t to the -9 times y. That's going to be equal to the right-hand side, 2 times 2000 minus 5t to the -8 plus c. Getting the y by itself, we're going to multiply both sides by 2000 minus 5t to the 9. When you do that, on the right-hand side, you're still going to get the 2. We're just going to have a single 2000 minus 5t left over, plus c, 2000 minus 5t to the 9. All right, we're not done, because remember we had those initial conditions. Initially, at time 0, we had 100 pounds of the additive. Don't forget that's what the y is representing here, the pounds of the substance. So we're going to set 100 for the y, and then 0 for my t. So I'm going to have 2 times 2000, which is 4000, plus c. If I plug 0 in for the t here, I'm going to get 2000 to the 9. That's some really obnoxious number, so I would probably just leave it like that. Subtracting the 400 over is -3900, and I'm going to divide by this 2000 to the 9. So this is some really tiny number, but that really tiny number is c, and we'll just leave it like that. So that means that my final answer here, y of t, is 2 times 2000 minus 5t. You could distribute the 2 if you really wanted to. plus the C, which is negative 3,900 over 2,000 to the 9 times 2,000 minus 5t to the 9. So that was just replacing the C with what we had found here. This still isn't done. This is the answer to that differential equation, and usually these are going to look pretty awful, but the question itself was asking how much of the additive is in the tank after 20 minutes. Our T was in minutes, so at this point we would just plug in 20 to get the final answer. And I'm just going to go to the book here and grab the book's answer. Maybe. It wasn't letting my finger go down. It's on the next page. Bear with me while my slow computer loads the next page. There we go. So it's around 1,342 pounds. Okay, great. So these are these mixture problems using the first order differential equations.